Welcome to the Robotics Through Science Fiction podcast. I'm Robin Murphy, and today we have with us Dr. Howard Chizeck, a professor in electrical and computer engineering at the University of Washington. He's a leading roboticist, and he loves science fiction. Howard, thanks for being here.
Oh, thank you. Good to be here.
Well, tell us about yourself and what you do with robots.
Well, I'm a professor, so I teach control theory and sometimes about robots, in particular capstone student design projects involving robots of all kinds. And then a portion of my research involves robots, beginning with robotic surgery, giving a sense of touch to the surgeons for robotic surgery. Because right now the robotic surgery systems don't have any sense of touch, so the surgeons are suturing without feeling the string. So you can imagine how hard it would be to tie your shoes if you couldn't feel what you were doing. That's what the surgeons are doing in robotic surgery. That then extended to other applications of haptics and vision. And that's sort of the robotic activity. And I also work in neural engineering, closed loop systems for essential tremor and Parkinson's disease and other indications.
And we're going to circle back to that. So you're an expert in telerobotics, and you started a company, Olace, that's doing quite well. And I think Olace is silo spelled backwards. Is that how it got its name?
Yeah, it's Olace Robotics. That's actually the second name of the company. We started as Blue Haptics, but then none of our products were initially haptic products, so we changed the name. And we do what we call progressive autonomy. So we're making software for other people's robots and other people's sensors, although we do sell an interface device, to provide telerobotics so that humans and robots working together can do tasks safer and more efficiently than autonomous robots are capable of, and that humans are able to do. So if it's something that's far away, or very cold, or very hot, or radioactive, or biohazardous, or chemically dangerous, or deep in a mine, or out in space, you're not going to send humans there, at least not easily and with safety. So sending a remote robot is a solution, but the remote robot won't have human judgment and adaptability. And so even if it has precise control and wonderful sensors, the capabilities of autonomous robots are just not there for adaptive tasks, new tasks. For example, working in space where things are drifting about. Robots are very good in a very structured environment. They're much harder to be autonomous when they're not in a very structured environment. So the company actually started because there was a request for proposal from a government agency to clean up unexploded ordnance on the bottom of lake beds. In its infinite wisdom, the government had done target practice in locations, and then when they were done, there were a lot of unexploded shells, and they tended to fill these up with water and make them recreational lakes. So fast forward a few decades, and people are diving to remove these things, which is not a good idea. And we saw a request for a proposal and said, oh, that looks just like robotic surgery. It's just teleoperation. Of course, the robots are different and the sensors are different. But we got a seed grant for that, and out of that grew the company. And so our first product line and first set of things has actually been for underwater robotics. For example, if you make a cable connector underwater, the connector costs $30,000 because of its pressure and connection. And if you break it, you not only pay $30,000, you pay $1 a minute ship time to bring it to the surface and bring it down again. And the failure rate is really high for human operators driving ROVs from the bottom of ships.
Yeah, we saw that at the Macondo oil spill. We had
Yeah.
some major collisions between the robots being operated, taking out, damaging the cap that they put in. So it's really a challenge. And underwater, I think makes it even more obvious to people who haven't thought about it for things like disasters or nuclear space. Now, Howard,
And
oh, go ahead.
well, I was just going to say what we get from it is the human operator is still controlling the robot, but now it's kind of like driver training wheel. As it gets close to where it's supposed to go, there's a gentle pushback or a gentle guidance.
Yeah.
So a less skilled person can quickly do what needs to be done. So it reduces the risk of failure. It reduces the complexity for the operator and the training time. So that's sort of where the company is. And the trick for all of this is new sensors, rapid processors to deal with the sensor information. And for the company, it's finding things that people actually want to buy. Because as you know, a lot of robot companies have failed because they made products and then not had a market.
Yeah, I think there's that, a graduate student does something just really brilliantly innovative. I had one call me who's like, look, I've made rotor blades for quadcopters that are 2 orders of magnitude more quiet. This will be perfect for emergency response, won't it? No, not really. That's not a problem. But going back to this idea of teleoperation, of course, that's the dominant form of how we do things in disaster robotics. But I've heard artificial intelligence researchers just very snidely refer to telerobotics as a degenerative case of robotics, that robotics should be fully autonomous and the teleoperation stuff is just a stopgap until the AI gets better. What are your thoughts on that? Is that what you're striving for, full autonomy, or do you look at having this shared progressive autonomy paradigm?
Well, it depends on the application. If you're controlling a robot on Mars, you need a lot of autonomy because the round trip time for the communication is too long for teleoperation. If you're in low Earth orbit and you're only talking about a second or two delay, it doesn't really matter. There are ways around that. So I'd start by saying that the claim that telerobotics is a stopgap, I would say, well, for what application are you talking about? Because sometimes you must have autonomy and sometimes it makes no sense. Okay, I mean, if you wanted to pick up a pencil and write, you wouldn't use a telerobot for that, right? You wouldn't use any AI except what's in your brain. The second thing I would say is that AI is just not that good yet. If you have thousands of training examples or you simulate training examples and you do your deep learning, your convolutional neural network, you can learn a task really, really well. But then suppose you're on the International Space Station and something floats by and gets in the way. You're stuck. Your AI system won't be able to do it because it'll be outside the training set. So it might be that AIs will get good enough for certain tasks, and then it'll be a question of does it make sense to give that control to the robot or not. I think also we will see a lot of human robot teams doing things in space and underwater, where the real trick is going to be the communication between the robots and the humans so they can coordinate tasks together. And so the whole area of co-robotics, I think, will grow faster than fully autonomous AIs. And I think funding activity from governments and industry already show that.
Yeah, and that co-robotics, that teaming has always been a near to my heart because that's what I see. It's a shared. So given that, how do you decide what to share or delegate to a robot? There's so many different paradigms: sharing control, trading control. There's a lot of arguments in the scientific literature for those. Do you have a preference or a philosophy for you can explain to lay people?
Okay, so let's take an automobile as an example, since most people are familiar with that. Um, a fully autonomous car, you just sit there and you push a button in the beginning or tell it to start, and that's it. Uh, and that works well unless something happens that the sensors can't anticipate. For example, there's been a really nice paper. People put stickers on road signs and fooled the AI system, and then it didn't know what to do.
Yeah, they
Or
thought it was toaster, that the stop sign
right,
was a toaster. That was a great moment in computer vision machine learning.
yeah. So now the question comes: what do you do if you're the human in the car when you see that happening? Um, it's very easy for the automated part of the car to take over from a human, because all the velocity and directional measurements, all the sensor information is available to the automated system. It's very hard for a human to take over from an automated system because you can't instantaneously know all those state vectors, all that status information. We've seen that in a couple of airliner crashes where the autopilot wasn't working and they turn it off, but then the pilot doesn't know what's happening. Can't learn
The pilot
quickly.
doesn't have enough, and actually doesn't have enough, even if they know they don't actually have enough reaction time. Those
Right.
were the great studies from the 60s and 70s.
So,
Wickham's,
so switching
uh,
back and forth has
Arnett.
real problems. Um, and the problems are the transitions. How do you exchange the information between the automated system and the human pilot in particular? And if you're going between the human pilot and the automated system, the human operator may know things that the automated system just doesn't know about. So that's the challenge. So the approach we've been taking is to actually share the activity as you go along, so that, and again, now the human being does turn the wheel a little bit or push on the brake or the accelerator, but of course they're not actually pushing on a brake or an accelerator. It's an input to an electronic system which has learned things and knows things and works upon that. So we see that already happening on the market. If you buy a new car this year, if it thinks you need to stop and you've turned that option on, it stops for you. You're driving, but it stops for you. If it thinks you're going to pull out into a blind spot into somebody else on oncoming traffic to your left, it warns you or even prevents you. And you can set the speed and speed control right, and the cruise control, and it just does that for you. So we're slowly having these cooperative systems actually commercially available, where the human and the robot are working together. I mean, the car is really a robot. The car is a whole bunch of computers in a network, and with a few peripherals like tires and windshield wipers. And this has been our approach, is really to build the software to let the human operator and the robot work together with the sensors. And again, I would warn, it depends on the application, how much autonomy you can give to the system, or how much does it make sense economically and for safety to give to the system.
Now, this idea of sharing and what makes sense, who knows what when, and how fast it takes to engage that human out of the loop control problem is what's often called. Did that get you into neural engineering, and what is neural engineering from your perspective? Is that the brain machine interfaces that we're hearing so much about in the press?
Well, that's part of it. I mean, okay.
Big sigh, huh? Yeah.
Yeah, if you put an electrical device into the body to activate nerves or to activate muscle directly, then you're in the space of neural engineering. So that could be at the spinal cord level, it could be at the muscle level, or it could be at the brain. And I actually got into this in the 80s for paraplegic walking. If you go way back into, I don't know, 1985, 1987, you'll see some papers and a technology review paper, we were using electrodes, which later on were determined to be not reliable enough. But we're getting paraplegics to walk. People are still trying to do that in more efficient ways. Because there's a high societal emphasis on medical applications. What has changed since the mid-'80s is wireless communication, great batteries, power supplies, wireless recharging, very tiny electrodes, better actuators, but also a whole industry that grew up over pacemakers and defibrillators, implantable devices that electrically control or restart the heart. And building off of that, I got involved in about the last 10 years in using something like the pacemaker, but running it in the brain to control the tremor of essential tremor. And these, again, are available as clinical devices right now, but the patient goes into the clinic and the settings are set and that's it, and they go home. Stimulation is always on to suppress tremor. It creates side effects sometimes. We kind of said, let's do something different. Let's put electrodes on top of the brain. Let's turn up and down the stimulation only when it's needed. That reduces the stimulation, and the battery is surgically implanted, so you want to preserve battery. But also, stimulation has side effects. For example, stimulation for tremor can make it impossible to speak or difficult to speak. Well, if you want to stand up and talk, you don't mind tremor. If you want to drink a glass of water, you don't need to speak. Yeah. So having a system that can adjust between those would be very nice. Now, how does it adjust? Well, we have electrodes in the brain. Maybe we can get signals of the intention of the person as to what they want to do and use that to trigger the amount of stimulation. That could just be a single channel ramping it up and down. Okay, and that's a very simple brain-computer interface. Now,
that sounds like a very lovely one. Something, so many people I'm seeing having troubles with tremors and things like that.
That's one that's doable. Now, everyone has gotten excited because of great electrodes and advances in technology, and frankly, a lot of money from commercial and government sources into making brain-computer interfaces, the dream being that you could sort of think and do complex tasks. There's a problem right now. You just can't get the bit rate to generate enough characters for decent speech. Okay? And a lot of folks are working on it, including some famous companies. It is probably near the peak right now of its initial hype curve, and there'll be a curve down, and then it'll curve back up to wherever things are. But some applications are quite reasonable. If you pick up EMG signals that are going to what would be the missing arm in an amputee, and those signals then are used to drive the prosthetic, that's being done. And that gives you really nice prosthetic control for grasping. But the subject can't feel it. So now the next task is, can you get signals from sensors on the arm back to the sensory cortex? And there's some really nice products that people are making in that. Okay, so if you could give a sense of touch back so that the prosthetic felt like part of you, and if you controlled it just by thinking, just by doing, then that is a kind of a neural interface. Okay, and part of it's at the brain, the sensory part is, and part of it's really taking muscle signals that the brain has generated and sent down to the muscle. So that's an area where I think things are moving quickly. In terms of texting by thinking it, we're not there yet. And will that be 3 years, 5 years, 10 years, or 20 years? I really don't know. I do know that in 1982, I was working in paraplegic walking, and it's now 2019, almost 2020, and people are working on paraplegic walking. And right now, the exoskeletons, external structures, are better than neural systems. It's very hard to predict how quickly things will advance. But there's In the medical applications, there's a lot of push for it. Now, how does this interface with the robotics? Well, put a hat on. Let's use external electrodes, no surgery. Pick up signals, not complicated signals, maybe just
Right.
a
P100, something that's there. Yeah.
It's to put you through. It could be like a P300 or one of those things that's used for artificial speech right now. But let's use it to drive a robot in the home. Suppose you're quadriplegic, or you have Lockin Syndrome. You're sitting in a chair. The robot goes to the refrigerator. It opens the refrigerator, takes out the food you want, it puts it in the microwave. It brings it over to you and it feeds you. Okay. Somebody at some research lab right now is working on every one of those tasks for the robot with arrays of sensors and grasp. Okay. The cost of doing that right now would be prohibitive compared to paying for caregivers. But the possibility of giving a certain amount of independence to an individual by letting a robot that's reacting to their thoughts or their voice do things for them is certainly an opportunity. And in all these medical devices, you have to think about agency and autonomy. Some people would rather brush their own teeth or wipe their own bottom than have someone else do it. And so having a device that you can control to do that has a certain attraction. In this
and interact
field,
with the world, right? Because I mean, you referred to Lockin Syndrome. The great so far only two books by John Scalzi in that particular universe, but they're both great. Yeah. Talking about what happens if you are paralyzed and can't communicate or work, and then being able to work through surrogate robots.
Yeah,
kind of a nice idea, isn't it?
Yeah, or go to Neuromancer or any of these other things. I mean, if we're gonna do medical repair of broken systems, why don't we augment?
Yeah.
Why don't we snap in languages or skills and load them in and out? And there are people trying to do that. There's some interesting results in research labs, but the gap between something you can demonstrate once and something that's practical is very, very large.
Well, there's a lot of criticism about the demonstration environment, right? That we've and I thought Gary Marcus and Ernie Davis's new book, AI Rebooted, really takes to task a lot of the AI researchers for you got it to work once under pristine conditions. That is not the same as getting it to work in the real world. So.
It's worse than that. Some of the famous videos you've seen of robots jumping and doing calisthenics, that's trial 17 on that day.
Yeah. Exactly.
The typical case. So it's I mean, this is a challenge, right? The real world wants things that work reliably and safely, And to me, it's amazing that airplanes work as well as they do. I mean, we just get on them and and they fly, and they do it most of the time. They do what they're supposed to. We're getting that way with automobiles. I don't know whether we'll ever have fully autonomous automobiles allowed because there'll be regulatory issues. The lawsuits that will come from terrible accidents, when it'll be unclear whether it's the programmer is at fault, the manufacturer is at fault, the owner of the automobile, how you ensure that. There's a lot to get between where we are and where we'll be. But, I'm getting older, and when they take my keys away, I sure want an autonomous car to drive me there.
Yep, that would have been great for my father. Hey, we're running out of time, sadly. I know you love science fiction. Here's the big question. What's your favorite robot in science fiction?
I think I'm going to give you two. One is Robbie from the movie 1957 Invisible Boy. That was the second appearance of Robbie the robot. The first one being
from Forbidden Planet. Yeah. Yeah.
In the 1957 movie, Robbie is a good-hearted robot that saves the boy and the world and is his companion. And I urge people to find that and look at it. The reason there is the robot's got a soul. It's got
Oh.
spirit and a soul. And then I think the second is the advanced Bolo robots.
Yay, Keith Lomer. Yeah.
Right. So these are military robots that get bigger and better and stronger and autonomously defend planets. But then the war is long over and these things are buried and being used for agricultural, and sometimes they come to life. And the nice thing about those robots, a couple of the stories, is they have existential and moral dilemmas that they have to solve, and that gets explored. And that's a level of artificial intelligence that we're not at. But the treatment of that I thought was really very interesting. So,
and then Elizabeth Bear, of course, took it one step further when she did that brilliant story, Tideline, about a Bolo-like robot that passes on the Arthurian Legends. That was just really sweet.
Well, I mean, there's a couple of collections of Bolo stories by other authors as well. So people have explored that universe. The space stuff we're doing, I mean, Olace Robotics were involved in a moon landing in 2022 for scraping regolith with a repurposed Mars surveyor arm. This is the science fiction I grew up with. This is the Heinlein stuff that I grew up with. It's now coming to be, and that's kind of a thrill to see some of that happening. But those robots don't have the soul that the second Robbie appearance does.
I don't know, Mike from Heinlein's The Moon is a Harsh Mistress Had a Soul in there. But anyway, thanks so much for being with us, and look forward to talking with you. And let's get together and talk science fiction.
Okay.
And to all of you viewers, if you want to learn more about robotics, check out my book, Robotics Through Science Fiction, Artificial Intelligence Explained Through 6 Classic Robot Short Stories. And check out its big nerdy sister, the second edition of my textbook, Introduction to AI Robotics. And do remember to subscribe to our newsletter and our YouTube channel and all that, so you won't miss a thing.